Hello, this is Differential Manifolds, Magic Course 063. I'm Dm Kchm, and this is the first short video, and I'm going to say something about the general approach of the course and then say something about possible books. So first off, differential manifolds is a huge area. It's used in large areas of pure mathematics, large areas of applications and mathematical physics. It's one of the broadest topics in the whole of mathematics and its applications. What I'm aiming to cover is the basic topics, so smooth manifolds, smooth maps, tangent bundles, cotangent bundles, vector fields, differential forms, general vector bundles, and we'll do some more specialized topics at the end. And by the way, I'm using the word smooth, and I almost always will. Smooth simply means C infinity, differentiable of all orders, and it's a shorter word than differential or differentiable. So the course is differential manifolds, but I'll be talking about smooth things. What I'm aiming to do is give a working introduction to manifolds, so that you'll be able to read the literature, appreciate seminars, work with them yourselves. That doesn't mean giving all the details of all the proofs. There will be some proofs, but mostly I'll refer you to books or other places. For example, there's a great deal of analysis that underlies the theory of manifolds, and mostly I won't attempt to give proofs of that. I'll endeavour to give a clear idea of what the results mean and how to work with them, and a reference if you want to check on the actual details. So the other general point right at the start is that there's broadly speaking, there's two main approaches to working with manifolds. The more modern one is the global intrinsic method. It certainly goes back quite a number of decades now. It's historically associated with pure mathematics, but it's been extended into math physics and the applications of mathematics for at least 40 years. There are a lot of books setting out how to use the global methods of differential geometry in math physics in particular and various areas of applications. And the other method is to work with coordinates, and historically that's associated with math physics. It's philosophically, it's a different approach, but in fact, if you're used to the global formulation and you sit down to do an example, you'll almost certainly need to do it in coordinates. So in point of fact, it's best to use or to know both methods and use the one that's appropriate to the situation. And I'll endeavour to cover both. So something about books. These are three good books. Spivak, this is the 1999 edition, which is in good modern LaTeX and easy to read on the page. This is a very thorough, well-motivated, well-written, reliable book, strongly recommended. Volume 1 is really essentially concerned just with manifolds. The differential geometry in the strict sense is the subject of the other volumes. John Lee, a lot of people like this book. I personally feel that it's got too much in it, but I'll use it as a reference, and if you like this book, then it's certainly reliable, and it certainly has a great deal in it. Abraham, Marsden and Mathieu, these are three applied mathematicians. They've written this book explicitly directed towards applications. It's not all that recent, but it is very modern in outlook. The only thing to be aware of is that it does work with Banach manifolds. This really doesn't need to be a problem because you can just take Rn at every stage, and when you meet remarks about strong and weak conditions, you can simply assume that you've got the strong condition, because in finite dimensions there's no distinction between strong and weak. So this is certainly a good book. So all of these three are recommended, and I'll use them for references. These are some other books. At the top is Abraham and Marsden. This is a famous book, The Foundations of Mechanics. Two of the authors from the preceding one, but in fact Mathieu was also involved in this book. And so too was Alan Weinstein, whose influence you can see quite a lot of places. So this is 40 years old, or indeed more, but it still reads as a contemporary book. It's very, very accessible still today. You can choose to ignore the mechanics or investigate that, but as an introduction to manifolds, it's recommended. Conlon, this is a straight pure mathematics book. I've put down the first edition because I think actually that's better than the second, but make your own mind up about that. Conlon has more of the detailed proofs that underlie manifold theory. Warner, this is a famous book, now pretty well 50 years old. It was massively influential. It's now probably a bit too old-fashioned, a bit too concise, but nonetheless, it's probably a good idea to look into it at some stage. It was a very good book. Well, it still is a very good book, but it's perhaps done in a style which is no longer really current these days. Dwestermatt and Kolk, this is different to everything else. This is 2 volumes, and the subject is submanifolds of Rn. So not abstract manifolds, but the important special case of those that arise as subsets of Rn, well-behaved subsets. And it's a book that basically works by exercises. Each volume is 1/2 exercises and 1/2 introductory material. So again, I urge you to look at this, and if you respond to it, then it's a very good and reliable and carefully organised book. The exercise sets are grouped, they're cross-referenced back and forward. Some of them are easy, not many, but some. Some of them are difficult, but most of them are reasonably doable exercises. They're all very good. Then lastly, 2 books on curves and surfaces in R3. Presley is a fairly recent book, second edition in 2010. Kchm is an older book. It's very, very good, very concrete. It's come out in a Dover edition, paperback, a few years ago, I think 2016, which is a testament to its lasting popularity. Curves and surfaces in R3 aren't a main topic that we'll cover, but I'll refer to them from time to time as for motivation and as examples. So Presley or Kchm is definitely a good place to go to for that. Okay, that's the end of the first podcast.